Okay, so we're going to talk about, we have the likelihood is now Poisson. So we're talking about counts here. So f of y given lambda equals lambda to the y e to the minus lambda over y factorial. We want to show that the conjugate prior is the gamma distribution. Now, there's a few different ways of writing down the gamma distribution. We're going to go with the one that's g of lambda given r and v is equal to v to the power of r lambda to the r minus 1 e to the minus v lambda over gamma of r. Now, which bits of this can we ignore because they're only constants with respect to lambda? If you think about it, we can ignore this bit and this bit. They're horrible, but they're constants with respect to lambda, so meh. We don't need to bother about them too much. So we go prior times likelihood. And if you think about your gamma distribution, your Poisson distribution up here, you'll see, if you're thinking about it in terms of lambda, this y factorial is a constant. So this up here is proportional to lambda to the y e to the minus lambda. Your prior here is proportional to lambda to the r minus 1 e to the minus v lambda. Everything else constant with respect to lambda. That's your key bit. So prior times likelihood, well, if we're doing it formally, we have to include out all the horrible bits, so we will, just the once. So it's equal to v to the r divided by gamma to the r over times lambda to the r minus 1 e to the minus v lambda times 1 over y factorial lambda to the y e to the minus lambda. So what's that proportional to? I can get rid of everything that doesn't contain lambda in there and say I'll worry about that at a later point. Because Bayesian inference, in terms of, it's actually really only concerned with the shape of things. So the relative importance of different values. So exactly how high they are up in the distribution, lesser importance. So here it's proportional to lambda to the r minus 1 e to the minus v lambda, lambda to the y e to the minus lambda. And grouping similar terms together, you'd be getting this as lambda to the r plus y minus 1 e to the minus v plus 1 lambda. Now, what does that look like? Does it look similar to this? So something, some letter, minus 1. Well, we have that. And instead of v, we now have v plus 1. So this is a gamma lambda given R plus Y and V plus 1, which you can explicitly write out as V plus 1 to the R plus Y, lambda to the R plus Y minus 1, e to the minus V plus 1 lambda, over gamma to the R plus Y. That's having done all the integration. So what was our updating rule here? We start with a gamma distribution, or and V. They're just the parameters of the gamma distribution. We observe some counts. The number of counts you observe is Y. We've done a single trial, so we observe in one experiment, we observe Y counts. So we add on the number of counts to the R parameter and the number of experiments onto the V parameter. There's a slightly more generalized version of this that shows you how to do it to the N. If you observe this number of counts in this number of experiments, but we're not going to do that one today.